Section 3.1, Basic Probabilities and Probability Distributions, 3 Ways to Define Probabilities. So as we enter Chapter 3, we are switching gears, and we just finished up the 2 chapters of statistics that we're going to do in this class. As I told you in the very beginning, we look at lots of topics, but not very deeply in this course. And sometimes the topics themselves, it's like you're jumping around to different corners in the room, not really building upon what we saw before. But probability does have some good ties to statistics. There's a lot of things that you did in statistics that could be used in probability or rebranded for probability. One of them is the proportion concept. When you find proportions, like we found the sample proportion, population proportion in the statistics side, basically what you're doing there is you're finding the probability of either your population or your sample of having a certain characteristic. So at its heart, probabilities are really just proportions, and more importantly, they're just fractions. Probabilities, every single probability out there can start as a fraction. So, we'll see, more to that. There's more to it than just being a fraction, but the basic idea that I want you to understand is probabilities are just fractions when you're building them up from scratch. And then you'll do more with them as you move on. So in this section, we're going to look at understanding the basic probability terminology. Make sure you have the terms needed to work with throughout the chapter. Be able to find the probability when an experiment has equally likely outcomes. We'll see what that means as we get later into this section. And then compute the probability of the complement of an event. We'll see what that means. And last but not least, we'll create and interpret a probability distribution. And the probability distribution is going to look a whole lot like a relative frequency distribution that you saw in statistics. If you squint, you won't be able to tell the difference between the two. Because basically with your relative frequencies, you made fractions. You took the total there was, you divided the amount, or the frequency, I should say, of an occurrence by that total in order to get the relative frequency. Well, here you're still going to be dividing something by something else in order to get a probability. So it really is going to look very similar to what you saw with those relative frequency distributions when we start putting the probability distributions into play. So why probability in this class, and why would you care about it, or why should you care about it? Well, in your life, if you have insurance of any type, I don't care what type of insurance it is, health insurance, car insurance, home insurance, life insurance, any other insurance that you got out there, if you run a small business, you got to have liability insurance, things like that. Every single one of those rates of insurance, the amount of money you pay for your premium, somewhere probabilities were used to help that insurance company figure out the rate so that if so many claims were made, they could still stay solvent. They could still stay in business. That's why insurance is big business. There's a lot of money in that calculation of the rate. And, there's certain companies that are more cautious than others, and that's why certain companies have higher rates than others. So probability all day long in the insurance industry. And there's actually a branch of mathematics called actuarial science. If you looked at SOA.org, you would see some information in this. It's a really well-paying job, and it uses a lot of math. Not a lot of them in the world, but they basically figure out your insurance rates. They're at the heart of the calculations. And they also deal with things like pension plans. There's a lot of probability in that. As you start looking at the past historical trends of what has happened with, the stock market or bonds or, real estate investment trusts or whatever else you're investing in, the gold market, whatever it is you're looking to grow your retirement money in, whether it's a pension plan or, something that you're starting on your own. You use past information to help predict what might happen in the future, and again, try and plan so that your probability of having money when you get to a certain age and need it when you can't work anymore is high. So, probability all over with that. And then if you go to the local casinos, probability, every single gaming table that you're going to play at, every single gaming machine that you sit down and play, every single one of those games has probability at the heart of what's called the expected value concept. And I guarantee you, every single game in a casino is set up so that the house will win in the long run. Some people argue at craps because, they know people that can win at craps consistently. Well, even if that's true, the casino is taking what's called the rake off of all that. So they're still getting money from you. You just may not necessarily realize it right off top. They're going to massage those probabilities to make sure that when they take the cut, it's, they're getting their share, So, and casinos basically, in my opinion, are legalized stealing. I grew up in Las Vegas, and it's legalized stealing because every single game in there that you're playing is rigged against you. In the long run, you will lose more than you win, guaranteed. It's, if you win a lot, well, you're lucky, but there's 20 other people that are losing a lot to make up for your winning in a casino. So insurance, pension plans, and casinos, just right there, probabilities, in your life if you go to a casino, insurance for sure, I imagine. But that's why we covered in this class, to give you hopefully a little bit of insight into that world. So basic terminology, let's go ahead and take a look at this for a little bit. And in this chapter, we're just going to, as I said, look at these concepts related to probability. And I already talked about this stuff a little bit, how it follows from statistics pretty well. And, how in the casino, you're pretty much looking to see that casino guaranteed to win more than it loses. So moving into the actual terms here now. A random experiment is an activity or an observation whose outcome cannot be predicted ahead of time. So something like rolling a die, drawing a card out of a well-shuffled deck of cards, flipping a coin, all those things. It's random. You don't know what you're going to get. Even if you're very skilled at flipping coins, there's still a chance, unless you're just really good, that you don't know what's going to come up when you flip that coin. So, it's anything where you just don't know what's going to happen when you do it. The outcome cannot be predicted. So, a trial is one repetition of a random experiment. And, a trial could have more than one thing in it, where you're doing a succession of things in a row, and it's like, well, that's one trial. And then you do that whole succession again as a second trial. Something like maybe rolling a die, flipping a coin, drawing a card. You do those three things in a row, see what you get. That's one trial. Then you do all three things again. That's a second trial. So it's just one repetition of some random experiment that you're performing. And then the sample space is the set of all possible outcomes for a random experiment. And sample spaces can get very large in certain situations depending on how many things in a row you're doing. And we'll look at some of the numbers that go with that later. But in this class, we'll try and keep some of the things that you'll do with sample spaces on the manageable side. But overall, the sample space is just all the possible outcomes. For like rolling a die, the sample space would be 1, 2, 3, 4, 5, and 6. Those are the, for a normal die, those are the 6 things that you could see when you roll that die. Flipping a coin, you would see sample space is just head or tails. For a single flip of that coin, you're either going to see a heads or a tails. If you can land it on its edge, I get people that like to say this, oh, what about the edge? Well, you're really skilled and you should go into theater or, on YouTube or something. But I've never seen anybody in any of my classes be able to flip a coin and land it on its edge and have a stick there. So we're just going to assume heads and tails. And at any rate, so it's just a list of all the outcomes for that sample space. And then an event is a subset of the sample space. So an event is just a collection of outcomes. So maybe with a die, you're interested in seeing numbers less than 3. So there would be 2 outcomes, the 1 and the 2, that would satisfy that event. And events are a big focus of what we'll be looking at as we move through the different probability scenarios. So for example, if we are flipping a fair coin 2 times in an experiment, the sample space could be found using a tree diagram. I want you to be aware of tree diagrams here. So we're going to start with a root, and then we're going to go down here. When you flip a coin, there's 2 possible outcomes for the first flip. So I'll say here, on flip 1, you could have a head or a tail. It's the 2 options you get. And then you have off of the heads, off the first flip, you could have a head or a tail on the second. Just because you got heads on the first doesn't mean you're going to get the same thing on the second. You could get either. Same thing with tails. On the second flip, you could get head or tails after you flip that tail on the first one. So flip 2 would be here, and your different options depending on what happened on flip 1. So the sample space for this, the reason the tree diagram is nice, as you go down the branches and get to the ends, here, 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 and here, you will have all the possible outcomes for this particular experiment. So coming down the first branch, we would see, on the left here, we'd have heads, then heads. So HH, 2 heads in a row, could be one outcome for this particular experiment. And then we'll go down to heads, then tails. So HT, you get heads first, tails second. We've exhausted the heads on the first flip, anything that can happen off of that. So we move to tails on the first flip, and tails heads could happen. Maybe you get tails first, then heads after that. And then as you come down here, you get tails, tails. So you might be asking, well, tails, heads, heads, tails, does it really matter? And in probability, it is very important to, even if you're flipping both coins at the same time, you throw them both out there, you almost want to think like one coin is one color, the other is another, or maybe one's a nickel, one's a dime. Even if they're not, in order to get the proper probabilities for these calculations, you always assume that they're different and you want to count the distinctions between them. Like for heads, tails, it's like, oh, the nickel got heads and the dime got tails. And then for tails, heads, oh, the nickel got tails, the dime got heads. And it's important to make sure that you do account for all the possibilities in your sample space. And if you don't, you'll get the wrong probabilities when you go to calculate them. So that's why heads, tails, and tails, heads are there. You always think about it as though it's either in succession or there's 2 different things, and you want to make sure that each outcome for each thing is accounted for. Right, so on that note then, let's note something else here real quick, and then this will be the end of part 1. Part 1 had a lot of introduction stuff. So there's 2 outcomes for each, heads, tails for each flip. So 2 times 2 equals 4. We're going to come back to this a little bit later, see the multiplication principle, but I just want you to be kind of foreshadowed with that. You can take the number of possible outcomes for each thing that you're doing in succession, multiply it, and it'll give you the total number of outcomes that you would see in your sample space. I'll pick up in part 2 with the rest of this.